In Chapter 2, we're going to start talking about derivatives. And so in this video, we're going to talk about the problem that probably initiated the study of derivatives, or it could be one of the problems that initiated the study of derivatives. It's a classical problem. It's centuries old, maybe many centuries old. And the question is this: given a graph, a curve, how do we find the slope of the tangent line, or the line tangent to the curve, and what does this even mean? So here's a curve, and it's really not very curvy. It looks like a lot of line segments joined together. But what I want to do is I want to determine what the curve of the, what the slope of the curve is at this point, where x equals c and y equals f of c. So I will label that as c. And so you know that in algebra there is a slope formula, and well, we're going to use that, and that'll help motivate the definition of derivative. Alright, so I'm going to switch that c out for an x so that we'll have a formula in terms of x when we get finished. So what we're doing here is trying to find the slope of this curve at this point. So to use the slope formula from algebra, we need a second point. And so I chose a second point way over here. Now I'm calling this distance, this horizontal distance between the 2 points, delta x. You may be familiar with that notation. We use delta to mean a change, and so that represents a change in x. So if the initial point has an x coordinate of just x, then the new point has an x coordinate of x plus delta x. And so the y coordinates of these 2 points are what we get when we substitute the x values into the function. So here you're going to get f of x for the initial point, and for the new point you're going to get f of x plus delta x for the y coordinate. Now I'm going to draw a line between the 2 points, and we're going to call that a secant line. Now what do I mean by a secant line? Well, that terminology comes from geometry. If you draw a line that passes through exactly 2 different points of a circle, that line is called a secant line to the circle, or a line secant to the circle. Well, calculus aficionados have adapted that term, or adopted that term, to mean a line that is defined by 2 points on a curve. So you pick 2 points like we did, and then draw the line that passes through those 2 points, again like we did, and that is a secant line. Okay, so the next question we're going to ask is, what is the slope of this secant line? Well, the slope, remember, is the change in y over the change in x, or you can think of it as y1 minus y2 divided by x1 minus x2. So here's what I'm going to do. I'm going to write this as this x coordinate minus this x coordinate. So the y coordinate of the point on the right minus the y coordinate of the point on the left, divided by the difference of the x coordinates, which in this case is going to be the x coordinate of the point on the right minus the x coordinate of the point on the left. So that's going to give us f of x plus delta x minus f of x all over x plus delta x minus x, but this x coordinate minus that x coordinate, that's just delta x, which is what I had called it up here. And some of you may recognize this expression as the difference quotient. If you take a course called pre-calculus, you frequently deal with difference quotients. And so this is the slope of that secant line. And that's the question that I was going to ask here, but I decided to ask it in the other column. All right, so let's go on to this part. This says the choice of the second point is completely arbitrary. How can the second point have been chosen so that the slope of the secant line is a better approximation of the slope of the tangent line? Let's go back over here. I'm wanting to figure out the slope of the curve at this point, and I would say the curve would be, well, the graph seems to be going kind of in this direction, and so whatever the slope of that line is would be a reasonable approximation of the slope of the curve at that point. The slope of this secant line may not really be all that good of an approximation, and I think one reason for that is fairly apparent. I chose this point a long way from this point. We could have gotten a better approximation by choosing the second point closer to the first point, but how close is close enough? No matter how you choose the second point, you could always choose a point closer to the original point. So what are we going to do? Well, what we're going to do is we're going to use a limit. We're going to take the limit as this distance between the 2 points shrinks. Shrinks how much? Well, shrinks to 0 theoretically, not actually, because if delta x were 0, this expression would be undefined. But we're going to take the limit as delta x tends to 0 of this expression. And that's what we get right here. The limit of delta x, the limit as delta x tends to 0 of f of x plus delta x minus f of x all over delta x. That is how we define the derivative of f with respect to x. Provided that limit exists. So the derivative gives us the slope of the curve, or sometimes we say the slope of the tangent line at a given point. And we're going to talk about some notation. I've got a table of notation here. Fact, the derivative of f is a formula for finding the slope of the line tangent to f, and thus the slope of f itself at any point where the formula is defined. And so I've been using this term tangent line, and I've never really defined it. Well, the tangent line is what you get. Well, it's what this secant line turns into as this point moves closer and closer to the original point. And as we take the limit, this tangent, the limit is the delta x tends to 0. This secant line is going to turn into a tangent line. All right, so let's talk about some notation. There are two main notations we're going to use. There's the prime notation. So if you call the original function f of x, the prime notation for the derivative is f prime of x. So the prime is sort of like an apostrophe. Or if you're calling the original function y, then the derivative using the prime notation would be y prime. Now, this notation is also known as Lagrange notation. It is named for the mathematician Lagrange. I don't recall what his first name is off the top of my head. I don't know whether he was the first to use it, but he very well may have been. The second notation that we're going to use is known as Leibniz notation. Leibniz was one of the is considered to be one of the fathers of calculus. He's one of the founders. He and Isaac Newton were the first to prove what is now known as the fundamental theorem of calculus. They were working independently in the late 1600s, and they each came up with a proof for that fundamental theorem, and they are both given credit, and so they are considered to be the founders of calculus. So, in Leibniz notation, if y is the original function, then the derivative is denoted dy over dx. This is supposed to suggest the delta y over delta x that you use for the definition of the slope of a line. And if the function is denoted f of x, then the derivative is d of f of x over dx. You read this as the derivative of f of x with respect to x, or the derivative of y with respect to x. Or, if it's clear, you can just say the derivative of y. Ordinarily, in these situations, you're going to have y equals f of x, and maybe I should say typically you're going to have this sort of setup. And so this indicates that the dependent variable and the x represents the independent variable. And if it's clear what variable, what the independent variable is, then we might just say the derivative of y instead of the derivative of y with respect to x.